All right, I discovered over the weekend that my microphone crackles. So it's still going to crackle, but we'll get a new one, and then it hopefully will not crackle anymore now that I'm aware of the problem. Picking up where we left off last time, we were looking at ejected electrons. So we had, there's a diagram so I don't have to draw it. We had the photoelectric effect. We had light coming in. It was hitting this metal surface. The metal surface, if it was struck with the right light, would eject electrons. Those electrons would then be picked up by this positive terminal because they're negatively charged, they're attracted to the positive end, and we would see some current running. And we looked at this graph where our frequency of light, which is directly proportional to where the energy of the light, is on the x-axis. So left, low energy waves, low frequency, right, high energy waves, high frequency. And there's a threshold frequency. Once we got above that energy amount, now we are seeing ejected electrons, which is on the y-axis. So it suddenly jumps from 0 to now we're seeing some ejected electrons. And a brighter light, this top line, produced more ejected electrons than a lower intensity light, but they both started at the same threshold frequency. And we talked about the threshold frequency a little bit on this slide. So we had the kinetic energy of the ejected electrons was equal to the energy of the photon minus the binding energy, which we use this letter phi. So this is the minimum amount of energy it takes to knock one of those electrons off, to boom, blast it off. And the h nu here is the energy of our photon, and then the kinetic energy is just going to have whatever's left over. Let's make up an example that just has random numbers in it, 500 arbitrary units, 500 energy units from our light. Let's say that the binding energy is 150 energy units of light. I'm making them nonsense units because I don't want to do the real numbers. How much kinetic energy is our ejected electron going to have? It's just going to be the difference. So the kinetic energy of the ejected photon has 350 of these arbitrary energy units. It's just the difference. Whatever excess energy goes into the ejected electron. To give us an example, we can do calculations with that. We're now moving on to talk more about the wave-particle duality of light. So light sometimes behaves like a wave. It's got wavelength, it's got frequency, it's got energy related to those. At other times, it seems to act like a particle. Traveling through space. Like a really, really tiny thrown baseball. It'll travel in a straight line. Other times it behaves like a wave. And the behavior that you observe depends on how you test it. We'll see this after we talk about atomic spectroscopy. So when atoms or molecules absorb energy, like if you pump electricity into them in the form of one of these little lamps, then they can release that energy as light energy. Fireworks also do this. And each element emits a characteristic color when you've got it in one of these special lamps. So I think these are mercury, helium, and hydrogen, but I'm not 100% sure on the order. And they release different colors of light when you give them enough energy. If you take that light and you pass it through a prism, the prism does what? It separates. So it'll do the thing like that happens sometimes maybe around you, especially when it rains. You see a rainbow? That also happens sometimes when light passes through a glass at the right angle or it passes through shiny, sparkly gems. It can separate out the wavelengths and it can create a rainbow pattern. So when this emitted light from these different lamps passes through a spectrum, it'll separate out all of those wavelengths, and then we can look at the individual wavelengths of light. And the pattern that we see is called an emission spectrum. So this would be bands of light emitted by an energized element. So if you put enough energy in, it'll emit light. You send it through a prism that separates out all the wavelengths, and then you'll get a discrete set of lines that we'll see next. So when we're talking about emission spectra, this is what the process sort of looks like. We'll be doing something sort of similar to this today. So we're going to have these different lamps set up. Rather than passing them through a slit and then a prism and then collecting the wavelengths on photographic film, we are going to be using little handheld devices that'll have a slit in them, and then it'll separate out the wavelengths of light and set it up on like a little, basically a piece of film inside of the thing that we're using. So we'll be able to see these real time for different spectra. And if we look at different elements, like helium has a couple of lines, barium has more lines, oxygen has a little bit of kind of washout between the different colors, but it has even more lines, and neon has more lines than oxygen. And notice that like the lines don't show up in the same places. And there's also not the same number of lines. So that's why in the previous slide, it was saying that it's sort of like a fingerprint or a barcode. It's unique for each individual atom or element, both in terms of number and also where they're located. But they generally tend to be fairly spread out. There's also absorption spectra, which I believe would be this bottom one. We're not going to do anything with absorption spectra. You can also identify elements with flame tests, which I think we've got coming up in a lab, unless that's a Chem 20 lab, I don't remember. But you can take different elements in solutions like sodium, potassium, lithium, barium. You can put them into a solution, put them on a little piece of wire, put that over a flame and burn the element, and that gives it a lot of energy, and that will cause it to release a distinctive color of light as well. So when you go and watch fireworks around 4th of July, or just whenever people are setting off fireworks, when you look up in the sky and see all of the different colors, those different colors are from different elements. They're putting different mixtures of compounds into those fireworks to get them to produce those specific colors. That's part of the process for making the fireworks. So way, way back, Johannes Rydberg analyzed a lot of these atomic spectra, and he discovered an equation. The equation involved an inverse square of integers, and his equation is here. This is our Rydberg equation, or at least one form of it. We'll see something that looks similar to this again later in the chapter. However, this equation doesn't tell us why the atomic spectra are discrete. It doesn't tell us why we only have specific bands of color. Specific thin lines of color. It doesn't tell us why atoms are stable, because classical physics says that atoms shouldn't be stable. It also doesn't tell us why his equation works, so we'll be looking into some of the reasoning behind why his equation works. I'm going to rewrite this slightly. So we'll see something later, possibly in today's lecture, that has a similar form to this Rydberg equation. We'll also be using the Rydberg equation a little bit in our lab. Rutherford came up with a nuclear model of the element. In his model, the atom contains a tiny dense center called the nucleus. The nucleus is essentially the entire mass of the atom. It's positively charged. The protons and the neutrons live there. I don't know if this is explicitly part of Rutherford's model, but we know that now. So protons and neutrons are in the nucleus. The nucleus is positively charged because of the protons. The amount of positive charge balances the negative charge of the electrons, and the electrons move around. We could maybe make like a Jimmy Neutron type. If you've watched the TV show. The electrons sort of just fly around. I don't know that Rutherford talked too much about why they fly around. But there's some problems with Rutherford's model. Electrons are moving charged particles, and in classical physics, moving charged particles give off energy. So if the electrons are constantly moving around, they should be constantly giving off energy. And if they're constantly giving off energy, it makes sense that they would eventually lose enough energy that they crash into the nucleus and the atom would collapse. This is why we had that issue with why are atoms stable. They should also, because they're constantly giving off energy, they should be glowing. They should be releasing some sort of electromagnetic radiation that we'd be able to pick up, that we would be able to see. And so Rutherford's model is a little bit problematic for these reasons. So our nuclear model doesn't completely explain what happens when atoms gain or lose energy. Enter Niels Bohr, and Niels Bohr is going to have a much more long-standing model. It's one that I will reference back to regularly because it's a simpler model than what we're going to after this. So the Bohr model helps explain how the structure of the atom changes. What's happening inside of the atom that causes these changes? How is it adapting? How is it changing when it adds energy, when it releases energy? So in the Bohr model, we still have our nucleus, but the electrons travel around in orbits, sort of like planets in our solar system. The orbits exist at specific fixed distances from the nucleus. We'll see a diagram that's better than my drawing later. The energy of each of these orbits, each of these tracks, is fixed. So tracks, orbits, are a fixed distance from the nucleus. So that the innermost track is always going to be the same distance, the next track is always going to be the same distance, the next track is always going to be the same distance. And because they're fixed in terms of their distance, they're also fixed in terms of energy. So the energy is fixed or quantized, it's set to a specific amount. The amount of energy is related to the electron's position in the atom. So it's based on how close it is to the nucleus or how far away it is from the nucleus. So here's that better drawing of the Bohr model and some explanation for our atomic emission spectra. So electrons emit radiation when they jump from a higher energy orbit to a lower energy orbit. So for example, this electron here on our n equals 5 track, orbit 5, has higher energy, it's further away from the nucleus. We would call this an excited state. This is sort of you wake up Christmas morning, it's time to open presents, assuming that we open presents on Christmas and that we're excited about it. That's our excited state. At some point throughout the day, you're going to lose your energy, you're going to get tired, you're going to crash, Electrons also do that, and so this excited state is not going to last forever. It's a temporary state. Eventually, it crashes back down to, in this case, the n equals 2. And the distance that it traveled between these two is going to be fixed. So anytime it jumps from 5 to 2, it's always losing the same amount of energy, and so it's always emitting the same wavelength of energy, because the wavelength is directly related to the color and the energy. So distance between orbits is fixed. To lose energy, electrons must emit light. They release a photon or a packet, a little burst of light, anytime they make that transition. And in this model, the electron is never observed between states, between orbits. It's always observed in one state or another. Electrons only exist on orbits, on those fixed energy levels. The energies of those stationary states can be calculated from the wavelengths of the spectral lines. So if we know what the color of these lines are, we can figure out, we can relate the amount of energy for this wavelength to the amount of energy between two of our different levels. We won't necessarily know which two levels we're talking about, but we'll know that one of the jumps has that much energy, like this red energy. Blue-green is a higher energy color, so it's going to have a bigger gap, and then violet is going to be the biggest, so that's going to have a bigger jump related to it. And we'll be doing that in lab today. So the Bohr model is great. It's got some conceptual importance, but it was replaced by the more complete quantum mechanical model, which we'll be talking about next. I am still going to reference back because these orbits are really nice. I think they're easy to think about. I'm assuming that they're easier to think about for us than what we're going to talk about with quantum mechanics. So I'll often refer back to these orbit levels as a way of connecting us with the quantum mechanical model. Louis de Broglie proposed in 1924 that particles could have wave-like character in addition to their particle character. So they behave with the property of waves. They've got a wavelength. They've got a frequency that's related to the wavelength in addition to their particle character, where they just travel in straight lines. And the wave nature is most clearly seen in electron diffraction, which we're going to see on the next slide. They produce an interference pattern, which confusingly is not caused by pairs of electrons interfering with each other. It's single electrons interfering with themselves. So the electron is interfering with itself, which is really fun and not confusing at all. So this is that electron diffraction. So waves, we hopefully remember from last time, if you send waves through a board that's got two slits in it, the waves will go through the slits, they'll diffract, meaning that they spread out, and so they're going to create an array of different lines from there. We can think of it as different lines. And where those two beams overlap, they're either going to stack constructively, they're going to add together, or they're going to create these dark spots, which is destructive interference. Meaning they have the same energy, but they're out of phase with each other, and so they cancel out. So it was surprising to see that electrons also produce this interference pattern because waves produce this interference pattern. This means that electrons also have wave behavior. If the electrons behaved only like particles, then rather than diffracting through those two slits, we would expect them to just pass straight through those two slits. So this is what particle behavior would look like. We would just have bright lines where the light went through the slit. It wouldn't have diffracted at all. So this is what no diffraction would look like. But we see diffraction. I believe this is something you can also do yourself. We see diffraction, which means that they do behave like waves, which is cool. The wave nature of the electron is an inherent property of individual electrons, so electrons can behave like waves. De Broglie came up with an equation, the de Broglie relation, which we'll see on our exam. The de Broglie relation says that the wavelength is equal to the Planck's constant divided by the mass times the velocity. And I believe this is mass in kilograms. This is an equation that I will give you if you need it, but you still need to know how to use it. Knowing how to use the equations is the big battle for Chem 1. What's the correct equation? What do all the things mean? But the actual, like, where do all the numbers go? Where do all the letters go? That will be given to you. I believe this is also true. 1 kilogram meter squared per second squared equals 1 joule. Planck's constant has joules in it. We've got mass here on the bottom, so we have to use kilograms. So that the kilograms that's hiding in our Planck's constant gets canceled out by the unit of mass. That's why the mass has to be in kilograms. You'll also get this relationship, the 1 kilogram meter squared per second squared equals 1 joule. All right, let's use this relationship. We want to find the velocity of an electron. It has a de Broglie wavelength. That's our de Broglie wavelength, lambda, of approximately the length of a chemical bond. We're assuming that length is 1.2 times 10 to the minus 10 meters. I believe for this one we also need the mass of an electron. Which Google is kind enough to provide to me. So our equation, de Broglie wavelength, is h, which is Planck's constant, divided by mass, times v, velocity. It doesn't have the little front tail, right? No front tail on the v. That's how we know that it's v and not nu, which would be our frequency. We've got our wavelength, 1.2 times 10 to the minus 10 meters. H is a constant, 6.626 times 10 to the minus 34 joules seconds. Mass, I looked up, you would be given it if you needed it, 9.109, we'll stop there, times 10 to the minus 31 kilograms. Is there anything else that we need? No, there's nothing more that we need. We've got everything we need. We're solving for v, velocity. So we're going to rearrange, multiply both sides by v, divide both sides by lambda. We'll get v equals h over m lambda. I suppose one thing that might be helpful, 1 joule equals 1 kilogram meter squared per second squared for our h. This lets us cancel some units out, otherwise we're left with just a mess of units. So for h, 6.626 times 10 to the minus 34. We're transforming joules into kilograms meters squared per second squared, and there's also a times seconds. So the seconds squared on the bottom, one of those cancels out with the second squares that we have. On the bottom, we are putting our mass in kilograms. So that kilograms will cancel with the kilograms that's on the top. And now we put in our de Broglie wavelength. Our de Broglie wavelength, 1.2 times 10 to the minus 10 meters. And the meters here on the bottom cancels out the squared on the meters on the top. So the units that are left over are meters per second, which is units of velocity. So equals meters per second. We need our calculator. I would recommend for most of us putting parentheses around these numbers on the bottom when you're multiplying them. Add those in a different color. I get a large number, 6.1 for two significant figures times 10 to the 8 meters per second. That's a really big number. Does that make sense? I'm forgetting which famous person said it. I don't like it, and I'm sorry I ever had anything to do with it. One of our quotes from last class. I'll figure it out in post, maybe. All right, since quantum mechanical theory is universal, it applies to all objects, regardless of size. Therefore, according to the de Broglie relation, this one, a thrown baseball should also exhibit wave properties. Why don't we observe such properties at the ballpark? Any ideas? One possible answer, the baseball's mass is large, and so its de Broglie wavelength is minuscule and insignificant compared to the baseball size. Baseballs don't have any charge, so quantum mechanics don't apply to them. Or quantum mechanics are excluded, or baseballs are excluded from quantum mechanics? Any ideas? So it is A. The baseball's mass is large. And so its de Broglie wavelength is minuscule and insignificant compared to the baseball's size. The mass is not going to be really that close to 1, but it's going to be a lot closer to 1 than some of our other stuff. It's like an order of magnitude away from 1 at most. And the velocity is probably in the tens of meters per second. So it's basically going to have a de Broglie wavelength that's smaller than like the width of a nucleus. So you wouldn't be able to observe that because it's much larger than a nucleus. We also have an uncertainty principle. So with electrons, if you try to observe the wave nature, you cannot observe its particle nature. If you try to observe its particle nature, you can't observe the wave nature. It's sort of a Dr. Jekyll, Mr. Hyde situation. You get to observe or see one at a time. You can see the man or you can see the monster. I don't know which of these would be the man or which would be the monster. So the wave nature shows the interference pattern. The particle nature tells us about its position, because if it's a particle, then we know based on where it is and what direction it's traveling, we know where it's going to end up. If we know that, it will not also display an interference pattern, which is fun and not confusing at all. Big smile. So these are complementary properties. The more that you know about one, the less you know about the other. If you know a lot about its wave nature, then by the way that the universe is, you have to know very little about its particle nature. And there's this experiment that you can do where you shine a laser beam across where electrons are flying through, and this would give you some information about their particle behavior. So if you shoot an electron source through, you'll see bright spots, bright lines. You're not going to see the interference pattern. So the electrons behave as particles, and no wave behavior is observed. The big part of the uncertainty principle is we can know a lot about one and we wouldn't know about the other. We can know a lot about the other and we wouldn't know much about the one. Heisenberg, not from Breaking Bad, had an uncertainty principle. And it looks something like this. We're not going to really do anything with this relationship, but this is a mathematical relationship that we have. The more accurately you know the position of the electron, this is the uncertainty of position, that's multiplied by the mass and the uncertainty of velocity. These two things multiplied by each other has to be greater than or equal to Planck's constant divided by 4 pi. So if the uncertainty of the position is really small, then the uncertainty of the velocity has to be really big. If the uncertainty of the velocity is really small, then the uncertainty of the position has to be really big. So our big takeaway, we cannot simultaneously measure the position and the velocity of an electron. If you've got a an atom and you know the electron is here, you have no clue what direction it's traveling. If you have an atom and you know, okay, well, the electron is traveling a certain speed, certain velocity, then you've got no clue where it is, which is really fun. So this would be the takeaway. We can't simultaneously know where it is and how fast it's going. We can know one or the other to a good extent. See if we remember what we saw in the previous slide. Which statement best summarizes the uncertainty principle? We can know both the position and the velocity at the same instance. We can know either the position or the velocity at the same instant. We can know neither the position nor the velocity at the same instant. Ooh, we've got guesses for all of them. I hate that. No, but we got a lot of guesses, so that's good. What does the uncertainty principle say? We cannot simultaneously measure the position and the velocity of an electron. We can know one or the other. So A is out. It's a B angle. We can know the position, then we wouldn't know the velocity. We can know the velocity, we wouldn't know the position. We could also, of course, like most of us have been doing for most of our lives, know nothing about either of them, and that would also work. We talked about, I believe last class, determinacy and indeterminacy a little bit. So in classical physics, particles like baseballs, bullets, other projectiles, frictionless spherical chickens that are point masses move on a path determined by the velocity, position, and forces acting upon it. If you've taken a physics class, you've probably done some of these calculations. This is determinacy. The present state determines the future. This is you see a car driving, and moments before it hits a person, the video stops, and then there's some like monologuing on top of that. We know what I'm talking about? Let me draw a really bad car for us to help drive the point home. Wow, what an incredible car. It's an armadillo car. And a person about to get hit by the car. We know what's going to happen next, right? The person gets hit by the car. That's determinacy. Indeterminacy means that we would be able to guess with some statistics, with some probability, 50% of the time the car hits the person. Maybe this is like a magic world. Maybe we're in the Marvel universe. And suddenly, poof, a portal appears and the car is transported to somewhere else. It no longer hits the person. That would be more like indeterminacy. We can know the car is traveling really fast, or we can know that it's right next to the man. We can't know both at the same time. That's our indeterminacy. Basically, we just don't really know everything. And so instead, for our electrons, we use probability distributions. We use statistical functions. And to really look at those in depth, we have to use calculus. You haven't taken calculus, more than likely. So lucky for us, we don't invoke calculus. We're just going to look at it very briefly. Here's the classical concept of trajectory. This would be determinacy that we were talking about, or a deterministic outcome based on the trajectory, the position of the ball, where it's traveling, the force of gravity. Maybe there's a little bit of wind. For a really good outfielder, we can get under that ball and catch it. That's our classical trajectory. In quantum mechanics, which replaces the Bohr model, that's the one with the nucleus in the middle and the different tracks around it that we looked at earlier. The quantum mechanical replaces that, and we would instead get a probability distribution. So we know that it's probably going to hit the strike zone in this case 40% of the time. 20% of the time it'll be really tightly grouped. 70% of the time it's going to be sort of roughly in that area. They're all of these pitches, by the way, would be leaving the pitcher's hand the exact same way every single time. So like if if you put a pitching machine down and you just fed balls into the pitching machine, ideally it's basically right down the middle of the plate every single time. In a quantum mechanical model, it can go anywhere. Like 1% of the time it ends up going the wrong direction, maybe. Probably less than 1%. For our electrons, energy and position I think this is relative to the nucleus, are complementary. Kinetic energy generally is 1/2 mv squared, where m is mass and v is velocity, meters per second. For an electron with a given energy, we can describe it in terms of an orbital. Orbital replaces orbit. So orbital is our quantum mechanical term. This replaces orbits, which are from our Bohr model. So instead of nice, neat little tracks, we've got essentially shapes. Orbitals are shapes. They're actually probability distributions, but we see them and we think shapes. I see them and I think shapes rather than a probability map. We should also know they're a probability map, but we can just say that they're shapes because that's really what they are to us. All right, here's all that we're going to look at Schrodinger's equation. Schrodinger was the guy that had the cat. He put the cat in the box. I don't think he actually did this experiment, but it was a thought experiment. You put a cat in a box. There's poisoned food in the box. I think there's also good food in the box. After some amount of time, we assume that the cat has eaten some of the food, and it's either dead or alive. At any point in time, we do not know if the cat is dead or alive, and so it's both dead and alive until you open the lid of the box and you see, oh, the cat is dead because it ate the poison food, or, oh, the cat is alive because it was a smart cat. Must not be an orange cat, and it didn't eat the poisoned food. No shade to anyone that has an orange cat. They're wonderful, but they do tend to be dumb, according to the internet lore. If you want to scare yourself, maybe, it's not the right season for it, you can go look up Schrodinger's equation. You can look up the quantum mechanics Wikipedia page, and you'll feel like you've stumbled onto the wrong language, because this is the most simplified version, basically, of Schrodinger's equation, and then it gets more complicated from there. But basically what Schrodinger's equation does is it lets us calculate probability, and when we can calculate probability, we produce these things called wave functions, and we square the wave function, whatever that means, and that represents an orbital. We can calculate, based on Schrodinger's equations, we can calculate orbitals. So this is the basis for which we get orbitals, and remember I've talked about orbitals are shapes. We'll see some pictures of those shapes very soon. Calculations show that the size, the shape, the orientation in space of one of these shapes, these orbitals, are determined by 3 integer terms in the wave function. So there's 3 separate terms that go into this function that spit out your probability map, that spit out a specific shape. And these integers are called quantum numbers, and you need to know what these quantum numbers are. So our firstest principal quantum number is n. N is the same, this principal quantum number is the same as n in the Bohr model. And we'll do a really poor drawing of the Bohr model here for you. So n refers to the orbit that we're on in our Bohr model, which generally refers to our energy level that we're on. This also applies to quantum mechanics. So n equals 1 is our lowest energy, n equals 2 is more energy, n equals 3 is outside of that, that's more energy. This applies over from the Bohr model. They're analogous for this. So that's our principal quantum number. I'm often going to abbreviate quantum number as Qn to save space and time. We also have the angular momentum quantum number, and then underneath that, the magnetic quantum number. And these first three quantum numbers are related to each other. So based on our principal quantum number, we have a set number of angular momentum quantum numbers we can have, and we have a set number of magnetic quantum numbers that we can have based on that one. And then separately, we've got our spin quantum number. So m sub L is magnetic quantum number, m sub S is spin quantum number. And we're going to talk about each of these on their own individual slides coming up. All right, our biggest quantum number, principal quantum number. Principal like the head of the school. Same idea? This is our big quantum number. This is like orbits in the Bohr model. This determines the overall size and energy of the orbital. N is any number that's greater than or equal to 1. So n equals 1, 2, 3, 4, ... sort of caps out at 7. Sort of caps out at 7. As you get to these higher numbers, you get to be higher energy, and we're also going to have larger orbital size, like with our Bohr model. So our n numbers here in green. For hydrogen, we've got this number. It's not something that you need to memorize. Basically, this just lets us calculate the energy of any of these orbits or principal quantum numbers. We can really only do this for hydrogen. The energy here up front is negative. Because the positive and negative charges stabilize each other. So the electron that's flying around on the orbit, really flying around in some other way, rapidly, randomly. But if we think about it with the orbits, it's flying around in these orbits, it's got a negative charge. In our nucleus, we've got a positive charge. And the interaction between the positive charge and the negative charge stabilize each other. The same way that two magnets, if they're positive and negative ends, you bring them close to each other, they want to be closer. They want to pull in. They don't want to repel each other. That pulling in is why we've got the negative here. When n gets larger, our electron gets further away. So the magnetic force between these two is going to get smaller. It's a further distance to the electron and the nucleus, the protons, because they're further away, have less attractive force. It's less stabilizing. It gets less negative, which means it's more positive. Still fun, still not confusing at all. Do we have questions so far about any of this? Rydberg equation, de Broglie wavelength, Bohr model, quantum mechanical model. Question?
When you say when n
So when the electron bounces out to a higher orbit, that's when the energy it's less stabilized. So the energy increases as we go to these higher levels. It's the same electron. Or we could compare an electron on a high, like really far away, versus one that's really close. So if this is our nucleus, this should get closer. If this is our most stable point, then the electron here on this n equals 2. I don't know why I put less stable. And then on this outside one would be the least stable, because it's the furthest away. When two magnets are really far away from each other, they don't interact very strongly at all. Sort of a similar thing going on. Does that answer your question?
So the least stable area would be when it gets less negative? Is that what you're saying?
Yes. Okay. It's a more positive energy or less negative. The bigger negative number means that it's more stable. And here's what those principal energy levels look like for hydrogen. So for n equals 1, we've got that constant that we saw times 1 over n squared, where n is 1. And so we just get this number back. When we go up to the second energy level, this is minus 2.18 times 10 to the minus 18 joules times 1 over 2 squared. So it gets cut in fourth. And then this one is 1 over 3 squared, which is 9, 1 over 4 squared, which is 16, and so on and so forth. The n levels, the principal quantum number levels, get closer. I guess the energy levels of those get closer as n increases. That's an important distinction for these. So our n equals 1 to n equals 2, big jump. N equals 2 to n equals 3, smaller jump. N equals 3 to n equals 4, even smaller jump. So the spacing of these energy levels gets smaller and smaller the higher that number gets. So that's our principal quantum number. Our angular momentum quantum number is our next number. And this is also an integer. It's a positive or negative whole number that determines the shape of the orbital. I would call this shape family. Sometimes I think we also call it subshell. And we could also think of as the shell. So in the Bohr model, our little orbits, those would be our shells. So this is inside of one of those levels. And L, our angular momentum quantum number, has integer values from 0 to n minus 1. So when n equals 2, L can be 0 or 1, which is 2 minus 1. So at 0, we can have 1, we can have 2, we can have 3, and these correspond to different letters. You should have learned these letter designations if you took Chem 20. So they're S, P, D, and F. We're just also learning that L has numbers associated with each of these. So L equals 0 is our S subshell. L equals 1 is our P subshell. L equals 2 is our D subshell. L equals 3 is our F subshell. We're in the learning the board game that your crazy friend who plays lots of board games wants to teach you part of the class. I'm teaching you my crazy board game. What values of L are possible for n equals 3? Our rule is that L can have integer values from 0 to n minus 1. It can have whole number values from 0 to n minus 1. What's n equal to? N equals 3. We're always going to have 0 as an option. We've got 0. What's n minus 1? Equals 3 minus 1, which equals 2. So the numbers, the counting numbers that we can get to from 0 to 2 are 0, 1, and 2. So C would be the correct option here. Typically, I do give an exam question. I think I've done this primarily as a short answer question, but there's also going to be multiple choice questions about these different quantum numbers. So if you've got, n equals 2, what are all the L values? What are all the M sub L values that you can have for that as a free response question? We'll also see them probably showing up as multiple choice questions. Okay, our third quantum number. Our magnetic quantum number. Our magnetic quantum number specifies the orientation of the orbital, or a specific orbital / shape within a subshell or shape family. So for n, our principal quantum number, we were talking about the orbits. We were talking about the different energy levels. For L, our angular momentum quantum number, we were talking about subshells. So within that shell, there's different families of shapes that we can have. Our magnetic quantum number is saying which of the specific shapes in that family are we talking about. So for S, P, D, and F are 4 letters, or L equals 0, 1, 2, or 3. We've got different shapes within those sets of families that we will see pictures of. And M sub L is referring to which of those specific shapes do we have. M sub L goes from, it's based on L, so it goes from negative L to positive L, and this includes 0. So if L equals 1, M sub L equals, it's got a couple of possible values. It's got negative L, which would be negative 1, up to positive L, and it includes 0. So negative 1, 0, and positive 1 are options for M sub L. I think that this is good flashcard material, this quantum number stuff. So knowing how we get our values for m sub l, how we get our values for l, what our options are for values for n, all good flashcard material and stuff that I'd be happy to review with you again. We might go over it again at the end of the slides today. If we have L equals 2, our angular momentum quantum number is 2, what are the magnetic quantum number options? The correct answer here is D. M sub L goes from negative L to positive L. It's whole numbers, integers, counting numbers. Those are all slightly different sets, but sort of convey the same information. Hopefully to us that it comes through. So -2, -1, 0, +1, +2 would be our options. That means D is the correct answer. How many numbers, how many options do we have for m sub L? What's the number of numbers that we have? 5 numbers. Five numbers means 5 specific shapes within the shape family. Okay, and then our last quantum number, the spin quantum number, this one's separate from the other 3. There's 2 options for spin quantum number. This is separate from the other 3 quantum numbers. The first 3 quantum numbers, n, l, m sub l, are all dependent on each other. So n, integer or counting numbers starting from 1, counting up. L goes from 0 to n minus 1. M sub L is negative L to positive L. These 3 are all related to each other, and spin quantum number just has 2 options. It's related to the minus 1/2. The options are up or down. They'll come into play a little bit later on. They are actually formally called upspin and downspin. All of our electrons are going to have the same amount of spin. That's why they're always +1/2 or -1/2. It's just sometimes they're spinning one direction, other times they're spinning the other direction. Do you have any questions about our quantum numbers? So being able to draw out, write out, and know how to use like this little section that I gave you here could be very helpful for the exam. Now let's look at orbitals. So each individual combination of n, principal quantum number, L, angular momentum quantum number, and m sub L, magnetic quantum number, describes one orbital. And orbitals are a specific shape, what I've been referring to as one specific shape. N is our shell, L is our subshell, m sub L is the specific shape or the orbital. Orbitals that have the same value of n are in the same principal level or principal shell. If N and L are both the same, then they're in the same sublevel or subshell, or the other thing that I've been calling it, shape family. Shape family is just because I think that's a little bit more relatable to connect the idea to what we're hopefully going to come to be able to recognize. There are some general patterns. So the number of sublevels, the number of possible values for L is equal to N. When N equals 1, L is equal to 0. When N equals 2, L is equal to 0 and 1. We've got two options in N equals 2, two subshells. In N equals 3, we've got 3 subshells. And these also have letter versions, which you would have seen in Chem 20, S, P, D. There's also F, which is L equals 3. And then inside of these subshells or shape families, we've got an odd number of orbitals. Orbitals come in odd numbers. So if our L equals 0 has 1 orbital, 1 shape, P or L equals 1 has, jumping the gun, has 3 orbitals, D or L equals 2 has 5 orbitals. How many orbitals is F or L equals 3 going to have? Say it again? 7. Yeah, that's the next number in the pattern. Has 7 orbitals. So there's 7 different unique shapes in our F subshell or our F family. Sadly, we're still quite a ways away from seeing the actual pictures. But we can still play around with our quantum numbers a little bit. What are the quantum numbers associated with all of the 5d orbitals, and how many 5d orbitals exist? What's the first quantum number that we would come up with? Our principal quantum number, which has what symbol? N. And what is N equal to here? 5. So this number in front, this is our N. So N is 5. And then we're told that it's D. This is our angular momentum quantum number. D has a number that's associated with it. Do we remember what our symbol for angular momentum quantum number is? What letter symbol do we give it? L. And D corresponds to a specific value of L. What's the smallest value of L that we can have? 0 is the smallest number that we can have, and it goes up to n minus 1. For L, 1, 2, 3, 0, 1, 2, 3. These correspond to the letters S, P, D, and F. So we have D. That means that our L is equal to 2. And then what about our magnetic quantum number? Do we remember what that symbol is? M sub L. And what values of M sub L can we have when L equals 2? Goes from negative, positive. So our options are negative 2, negative 1, 0, positive 1, positive 2, spin, or M sub S always just has values of plus 1/2 or minus 1/2.